Learning to synthesize human motion from a given data distribution is a challenging task. The challenge is even greater when the dataset is highly diverse, unstructured, and unlabeled. Previous works in the domain focused on synthesizing a specific type of motion. Others proposed recurrent networks that are conditioned by a set of initial frames and are typically limited in their diversity. And others learn from a structured dataset and condition the synthesis by a label indicating a specific action. In this work, we present MoDi, a generative model trained in a completely unsupervised setting from an extremely diverse, unstructured, and unlabeled motion dataset. At the core of our framework lies a generative model that can unconditionally synthesize high-quality, diverse motions. The same generator produces these walking motions, standing up motions, falling back, and many more. Inspired by the exceptional performance of StyleGAN, our framework consists of a mapping network that learns to map a multidimensional IID Gaussian distribution to a disentangled latent space with semantic power. In this latent space, each point represents a motion sequence. The latent codes are converted into motion sequences via a hierarchical chain of structure-aware operators that are applied to the temporal axis while considering joint adjacency in the receptive field. In order to bridge the gap between unconditional synthesis in the imaging domain and the motion domain, we conducted a thorough study of potential frameworks, operators, motion representations, architectural variations, and more. For further details, please refer to the paper. Despite the lack of structure in the dataset, the learned latent space is structured and can be organized in clusters that are grouped by semantic similarity between motions. In addition, interpolation between two valid motions in the latent space yields a sequence of valid motions. A property that can't be achieved with a naive interpolation of the explicit motion representation. We can also use this latent space to edit motions in a semantically aware manner. An operation that can't be naively applied on the raw motion representation without degrading realism. Alongside the generator, we also propose an encoder that inverts real motions into our learned editable latent space. It allows us to complete partial motions, edit them, and fix unnatural or noisy motions. For example, we can predict a motion according to a prefix. Here we can see completion from different prefix lengths. Note the diversity in the two completed suffixes. We can fuse two motions together by first concatenating a prefix from one motion and a suffix from another, then use the encoder to project the concatenated motion into the healthy part of the latent space, and obtain an output motion that naturally transitions between the two motions. In this example, we concatenate backward-facing and forward-facing motions. Note how the output motion gradually rotates from back to front. Since the encoder projects motions into the natural motion manifold, we can denoise a corrupted motion. And even manually edit a motion in a naive way and let the encoder amend it into a natural one. For a given motion, we can also sample the neighborhood of the latent code corresponding to that motion. We can simulate an audience standing up to greet an honored guest, a group of friends jumping from a bench, or a crowd strolling in the town square. Here we show that the quality of our synthesized motions is better than previous approaches when the same setting is applied. Thank you for your attention.